Let's talk about this example. Okay, suppose you have your student loan of $5,000. This is not an unusual situation. This is actually something that is quite um, prevalent in today's society. People have loans. This is a real life example. It's what we call the mathematical model. Okay, so we have this loan of $5,000. The rate of the loan is 6.5% and it's compounded quarterly. Now, the loan is such that you don't have to start repaying it until you finish college. So suppose it takes you 6 years to finish college, and now you've finished your coursework and it's time to start repaying this loan. How much do you owe now? That is a very good question. And that we can find out by using our formula for compound interest together with our calculators. You could not do this without a calculator because of the number of times you're going to be doing the exponents that you're going to be doing. So either you don't need a graphing calculator, you need just a regular scientific calculator. So the first thing we have to do is designate what each of the letters stand for. Obviously, A is a final amount that we're going to be at the end of 6 years. The P is what we call the principal. And the principal is the original amount of money we borrowed, which was the $5,000. The next number we see is an R. That's the rate of interest. Now, the rate of interest is 6.5%, but we cannot write it as a percent. We have to change it to a decimal, which means move your decimal place 2 places to the left, so it becomes 0.065. The T is the total number of years you will have the loan, and you decided you're going to start paying the loan back after 6 years. 6 years is how many years we're calculating this loan for. You want to know how much we owe at the end of 6 years. And the final number is the N. Now remember, N stands for the number of times the interest is compounded or figured out each year. And that's where you have to look where it says compounded and figure out how many times. Here it's telling us it's compounded quarterly. Quarterly means every 3 months. How many times a year is that happening? Obviously, it's 4. If it would have said compounded monthly, we would have used the number 12. If it would have compounded annually, that means only once a year, we would have used N to be equal to 1. And now I'm going to put all these numbers into my calculator. So here's how I'm going to put it into my calculator. It's going to be 5,000 parentheses. There's a parentheses button on your calculator. You're going to put it in that way. 1 plus 0.065 divided by N, which we know is 4. Close the parentheses. And then we're going to go to our exponent button. And the exponent we're going to put is NT. Now, NT is, the N we know is 4, and the T is 6. So NT is going to be 24. That's what I'm going to put in that. That's the only thing I do sort of in my head, because I don't want to have 2 numbers there. And then you press equal. So we have 5,000 parentheses 1 plus 0.065 divided by 4, close parentheses, exponent 24. Obviously, you couldn't be able to do an exponent of 24 on your own. And this is the number that I got, 7361.7, and it's 89. Now, I always want to go to two decimal places because this is dollars and cents. So this would be an 8, but the number after that is a 9, so I round this up. So the total number I owe before I start repaying, even though I only borrowed $5,000, I now owe $7,361.79. So this is how we do this type of exponential equation. Again, notice we really needed our calculators to do this. Okay, so now let's continue from here. As I said, we're on the home stretch. Don't forget there is one final new assignment on Delta Math. You should be looking out for it. It's going to be the last assignment. I probably will also post a practice final for you. If it turns out that you do better on the practice final than you did on one of your other tests, I will probably exchange it. Let's say on the practice final you get 90, and on one of your other tests you got a 70. I'll use a 90 instead of the 70. As I said, I will be posting a practice final, but I probably won't count it as a test at this point. It's just going to be a practice for you, so you'll see what the final is going to look like. So let's go on from here. Don't forget that all your homeworks and tests and any kind of assignments that you have to be completed by Saturday, the evening, the 5th of December. We're at the last week of class. This is the week you have to complete everything, because I am going to start making up my grades at that point, and I need you to have everything turned in. If you have a problem with that, or you need an extension or something, you've got to let me know and we can discuss that. What we're going to be talking about today is something called logarithms. We started last week with something I will give I won't give it for a specific 2-hour time period. I will give the final so that you can take it at a time that's convenient for you. But don't forget, once you start taking the exam, you have to complete it in one sitting. But yes, it will be available, just like the midterm was. It'll be available. I don't know if it'll be on just a single day. It might even be available. I have to find out what they want us to do. But I certainly will give you either the opportunity to do it in the morning or the afternoon. You don't have to do it only at the I don't, and also I don't want it to clash with your work schedule, because sometimes that happens also. So I will be giving you some sort of leeway on that. Again, I'll let you know exactly when I know exactly what's happening. I'm hoping to hear the next day or two what's going on. Okay, so we're talking about logarithms. When we talked about a exponential equation or exponential function, we're dealing with something that looks like this. Here's a very simple one. Y equals 2 to the x. in an exponential equation or function, what we're going to know is the base, and the base will always have to be a positive number. And the variable is going to be in the exponent. So the base is going to be a specific base. The exponent, it might be 2, it might be a half even, it could be a fraction, but it can't be a negative number. The base has to be a positive number. And obviously, if I give you a value for x, you can give me a value for y. In other words, if I had written f of x is equal to 2 to the x, and I ask you what is f of 3, that would mean that you were figuring out what 2 to the 3 is. And 2 to the 3 you can do either on your calculator in your head, and you get the answer is 8. Or I could have asked you what is f of negative 2. And that would have been find 2 to the negative 2 exponent. And I know when I have a negative exponent, it needs to take the reciprocal. So that means really do 2 to the second power. And 1 over 2 to the second power is 1/4. Notice when my number was a negative number, my answer didn't turn out to be negative. It turned out to be a fraction. We will see every time we do something like 2 to the x, my answer will always be a positive number. The y always turns out, or the f of x always turns out to be positive, no matter what the exponent is, because the only effect of a negative exponent is not to make your exponent negative and not to make your answer negative. It just makes it into a fraction. Obviously, in this type of function, what I'm giving you is the value of the x, the value of the exponent, and you're giving me the answer you get by putting the number to that exponent. Now, what if we want to look at this from a different perspective? Suppose I gave you the y. Suppose I told you that I'm giving you y is equal to 8. Could you give me the x? Well, then I would be doing 8 equals 2 to the x. And I'm basically giving you the answer and asking you, what is the exponent that I should put to 2 in order to get to 8? Now, that's not a particularly difficult question because the numbers are relatively simple. 2 times 2 is 4, times 2 is 8. Obviously, my x would have to be 3. This is asking the inverse, the opposite question, because now I'm not giving you the exponent. I'm telling you what the final answer is and asking you for the exponent. It's like I'm giving you the answer and asking you what is the question. That's what an inverse is. And when we have that, sometimes instead of writing it in the what we call the exponential form of the equation, we can write the equation in what we call the logarithmic form. The logarithmic form of an equation is giving us the exact same information that the exponential form does, except it's focusing on getting the exponent as opposed to getting the final number when you have the exponent. This written in logarithmic form would have looked like this. We write the word log, log, which is a abbreviation for logarithm. We then put in the base. Now the base here is written as a subscript. In this case, my base is 2. Next to the word log, not the exponent, because the exponent is a subscript, we put the number, the final answer that we have, which is the 8, and set it equal to the exponent. This says the same thing as 2 to the x equals 8. These two statements are identical. It's just focusing on a different place. Here, we have the base and the exponent, and we have the final answer. Here we have the base and the final number, and it equals the exponent. It's when we are looking to get the exponent. That's what the logarithmic form gives us. It's the same information given, focusing on a different aspect of this. A lot of the questions asked about logs or logarithms, if you want to call it logarithms, actually can be just answered if you can switch from the logarithmic form to the exponential form. Everybody is familiar with 2 to the x equals 8. It's not so familiar when you write log base 2 of 8 equals x. But let me tell you how to read this so that it will make sense to you. The word log is really another word for exponent. It's called log because it's not in the exponential form, so we're calling it log. The log, which is the exponent, that you put on the number 2, that you put on the base, to get the answer 8 is x. In other words, we're trying to figure out what exponent should we use to get this answer. Let's say I wrote this. Log base 7 of 1 over 49 equals -2. Let's try and interpret what I just wrote in terms of what it means exponentially. I'll do it again, and then we'll do a couple of examples, and I'll give you some to try. Suppose I want to switch this from the logarithmic form to the exponential form. So remember, the subscript is the base, so my base is going to be 7. The exponent is the number that's on the other side of the equal sign. Log is another word for exponent. The exponent equals, so the exponent is -2, and that equals the number that's right next to the word log. So in exponential form, what this is saying is that 7 to the -2 exponent is equal to 1 over 49. And of course, we know that that's true because the negative exponent means to make it into a fraction. And the 2 exponent tells you square is 7. So 7 squared is 49. So this 7 to the -2 is 1 over 49. I could go do the other thing. I could have something written in exponential form. Let's say I have 10 squared is 100. That is a statement in exponential form. What would this look like in logarithmic form? So let's remember, it's log. The base is 10 in this case, so that's my subscript 10. The number that goes next to the log, the word log, is the whole answer, the final answer, which in this case is 100. And that has to equal the exponent, which is 2. Again, log base 10 of 100 equals 2, means that if I take the base 10 and put it to the exponent 2, it's going to give me 100, which of course we know. By the way, you might notice on your calculator that there is a button that says log. That button is not just any log. It's something called a common log or a common logarithm. And it means that the base equals 10. So that button on your calculator will be great if you have a question and the question has to do with a base 10. If it's not a base 10 question, it's not as helpful. Notice also, because base 10 logs are what we call common logs, and the reason is because our whole number system is based on 10. Sometimes this is written just log. In other words, if you see the word log and there's no subscript written there, it wasn't that it was forgotten. It means that it's a common log, and it means that the base is understood to be 10. And it means that you could go to your calculator. And actually, if you go to your calculator and you press the log button and you put in the 100 and close your parentheses, you will in fact get 2. Because the log of 100 in base 10 is 2. 10 to the exponent of 2 gives you 100. So that's, we will occasionally use our calculators, but again, it's used only in various, in specific situations because it's only a base 10. There are ways of getting around it, but that's beyond the scope of this course. Okay, so the first thing we see is that actually logs are not something new. Logs are simply exponents. And if we know how to switch from our log form to our exponential form, it'll probably look much more familiar to us than it does in the logarithmic format. And many of the questions that are asked, let me see if I can find an old test. Just looking at an old final. And you could see a question that looks like this. Solve the equation. Here's this, it says solve. And it says this, log x equals -2. And it gives you solutions. No solution. $100, 0.01, and 1/2. So this is an example of a log equation, and they're asking us to solve this log equation. And actually, this is a log equation in which, I'm just going to leave this format up here, in which there is no base written in. But now we know when there's no base written in, it really means that it's base 10. So really what they're asking here is log base 10 of x equals -2. Now remember, I said most questions that have to do with logs can be solved, not all of them, but many of them can be solved by simply switching from the log format to the exponential. Again, we're much more familiar with the exponential, so therefore we're more likely to understand the question if we put it in exponential form. Now remember, if we want to put this in exponential form, we're going to take the base, which is 10, we're going to put it to the exponent, which is what the log is equal to. In this case, it's -2. And that's going to equal whatever is next to the word log, which in this case is x. So I have to do 10 to the -2. Now, either I can do it in my head or I can do it on my calculator. If I do it in my head, 10 to the -2 means 1 over 10 squared, which means 1 over 100. And they don't give us 1 over 100, but we know 1 over 100 is the same as 0.01. 0.01 means 1/100th, so it's the same as the fraction 1 over 100. Remember, decimals are just a way of writing fractions in a quick way. Or another way we could have done it is just do it on our calculator. We could have done 10, pressed our exponent button, and put in -2. When I do that, it gives me 0.01, which again is the correct answer, 3. So turning it from the log format to the exponential format was a way of solving this equation. Okay, I'm going to give you a few problems to try on your own while I take attendance, and then we'll go on from there. I'm just going to put on the top the meaning of if I have log base b of a equaling c, that means the same thing as the b by base to the exponent c, the number on the other side, equaling a. So these two things mean the same thing. This is like our dictionary. This means this. Okay, so first of all, see if you can do this example. Okay, first, the first two are just switching. Write this in exponential form. Write this in logarithmic form. Okay, and then answer these two questions. Find okay, and I'm going to be taking attendance right now. Okay, so let's look at some of these questions and see if we can come up with the right answers. Just turning on the light here because it's. Did that affect anybody? It's very dark in my house, so I turned on my light. Dominic, okay, let me just change. No, a minute. Okay, so number one, we wanted to switch this from the log format to the exponential. So we know our base is 5. Our exponent is the number that's on the other side of the equal sign. The log is the exponent. Exponent equals. So my exponent is -3, and that equals 1 over 125. So that would be the exponential format of this logarithmic equation. The second one is in exponential form. We want to put it in log form. So here's my log form. It's log. Now remember, the subscript is the base, which in this case is 2. It's equal, the exponent is equal to 5, so that's what the number that's going on the other side of the equation. And next to the word log is the final answer, which is the 32. So this says log base 2 of 32 equals 5, which we could read, if you read it this way, it makes sense. Log, which means the exponent you put on the base 2 to get the answer 32 is 5. Okay, number 3, we're going to put that in exponential form and see if it makes it easier for us to find the answer. So the base is 2. We don't know what the exponent is, so we're calling it x, and that's going to give us 128. So I want to know how, this is what's called an exponential equation. We want to find out the exponent. How many times do I have to multiply 2 to get 128? So we could do that either on our calculators, just try multiplying the 2 number of times, or just do it in our heads. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128. I had to multiply 2 7 times in order to get to 128. So my answer in this case would be 7. The number 4 one, we're again going to put that in exponential form. So again, my base is 3. My exponent and the number on the other side is -2. That's going to be equal to my x. So I have to figure out what 3 to the -2 is equal to. And I know that when I have a negative exponent, it makes it into a fraction. So that really means 1 over 3 squared, which is 1/9. Remember, my answer, even though my exponent is negative, my answer is not negative because a negative exponent makes it into a fraction. It does not make it into a negative number. So notice all these questions would have been easily answered once we switched from the logarithmic form to the exponential form. So you have to be able to go easily from one format to the other. Again, the logs is just a different format of things that we've already talked about. We talked about exponents. Now we're still talking about exponents, but it's in a different format. So now we're going to our next step, how to work with these logs. And we'll keep in mind that what the logs are exponents, so that when we work with them, we'll always keep in mind that what we're doing is actually working with the exponents. And there are actually four basic properties or four basically rules of working with logs, of doing the arithmetic on logs, keeping in mind that the logs are exponents. So in order to illustrate each of these rules that I'm going to give you, I'm going to write the rules. We're going to do with the examples in exponential form, and we're going to do them in log form. Okay, so let's talk about two numbers. Let's talk about number A, which is 1,000, which is in exponent. We're going to be doing logs base 10. We're going to be doing common logs, even though we could do any base logs. The reason I'm doing common logs is because the numbers are really usually easier to work with. 1,000 is another way of saying 10 to the third. And B is going to be our 100, which is 10 to the second. Now, what if I want to multiply A times B? In other words, I'm multiplying 100 times 1,000, which will of course give us 100,000. And in terms of tens, that means 10 to the fifth. Remember, when you're working with tens, the number of zeros actually tells you the exponent. 10 squared has 2 zeros. 10 cubed has 3 zeros. 100,000, which is 10 to the fifth, has 5 zeros. We could have done it just because we multiplied 100 times 1,000, but we could have also done it by doing 10 to the third times 10 squared. And since the bases are the same, we know in terms of exponents, when we multiply numbers, we're adding their exponents. So again, that would have given us 10 to the fifth. That's the exponential format. What if we had done this in logarithmic format? What if I did this? I want you to tell me, what is the log of A? Now, the log of A, remember, I didn't put a base here, so we understand it's to be 10. The log of 1,000, which is 3, because 10 to the 3 is the 1,000. The log of A is simply the exponent that you put on 10 to get to the number. We know the exponent is 3. Similarly, the log of B is 2, because B is 100, and the exponent that you put on 10 to get 100 is 2. In other words, by writing this in exponential form, I can see what the logs are very easily. The log of 10 cubed is 3, the log of 10 squared is 2. So what is the log of AB? Well, we know that AB is 100,000, which is 10 to the fifth, so its log is 5. So let's look what happened. We multiplied two numbers, but what did we do to their logs? We didn't multiply the logs, we added the logs. And the reason we did that makes sense when we realize that the logs are the exponents, and we know the rule is that when you're multiplying two numbers, as long as their bases are the same, you add the exponents. The logs are exponents, so that's why when we multiply numbers, what we do to their logs, if we keep in mind what we do to logs is what we do to exponents. So therefore, our first rule or our first characteristic or property of log is that if I have, call this number 1, the log, and it's with any base. I know I did it with base 10 because the numbers were easy to work with, but this works with any base. The log of A times B is equal to the log base B of A plus the log base B of B. When we're multiplying numbers, we're adding their logs. That's rule number 1. Let's do another. Let's go back here. We're using the same A and B, but now let's divide. What would A divided by B equal to? Well, we could do it either 2 ways. We can do 1,000 divided by 100, which is 10. Or I could have done it by the exponents. I could have done 10 to the 3rd divided by 10 squared. And I know that when I'm dividing numbers that have the same base, then what I could do is just subtract their exponents. So 3 minus 2 would give me 10 to the 1. In other words, if I do the log of A divided by B, it's going to be, well, let me go back the way I did it with the other one. If I remember, the log of A, remember we said was the 3. The log of B was the 2. And the log of A divided by B is simply the exponent of the 10 here, which happens to be 1. In other words, when we divide numbers, what we do to their logs is we subtract, because again, the logs are exponents. And we know when we divide, we subtract exponents. So here's my second rule. Log base B of A divided by B is the log of B, log base B of A minus the log base B of the B. It's the top minus the bottom. The log of the top minus the log of the bottom. In other words, when you have a fraction and you change it to logs, anything in the numerator is going to be positive, but anything in the denominator is going to turn out to be negative, because when you're dividing, you have to subtract the logs. Okay, now let's do another rule. So I'm giving them examples from this A and B, but then I'm giving the specific rules over here. The next rule has to do with exponents. Suppose I take, I'm going to use the easier number, which is B. Suppose I take, let me just rewrite this, that the log of A, I keep using this, was the 3, and the log of B was the 2. So you just want to keep it there. Suppose I wanted to take B and raise it to the 3rd power. So what am I doing? I'm doing 100 to the 3rd power. And I can certainly do that on my calculator, 100 times 100 times 100. I think it comes out to be 1,000,000. You can check it. Well, there is an easy, I could have done it this way. I could have taken the B as 10 squared and raised it to the 3rd exponent. And I know when I have something with an exponent and I raise it to negative the other exponent, what I'm doing is I'm actually multiplying the exponents together. This is the same as 10 to the 6th, which means it's 1 with 6 zeros, which again is 1 million. And again, the rule is when you're dealing with exponents, if you're starting out with something with it that's an exponent, and you raise it to a second exponent, what you do to the two exponents is you simply multiply them. How does that work in logs? Well, we know that the log of b is equal to 2. So the log of b to the third, we know, was equal to 6. Right? Because that's the exponent of the 10. Remember, we're not writing a base, so our base is 10. What did we do to the log of b to get to the log of b third? We simply took the log of b, which was my 2, and multiplied it by the 3. 3 times 2 is what gave me 6. In other words, when I'm dealing with logs, any exponent actually becomes a multiplier, or what we call a coefficient. In general terms, here's my third rule. The log base b of a to some exponent is equal to the exponent n times whatever the log was. In other words, our exponent moves from being an exponent to becoming a coefficient. That only happens when you're dealing with logs. Exponents become coefficients. So log a to the n becomes n log a, just like log b to the third became 3 times log b. And we could even go a step further. This next step is actually just an extension of what we just said. Let's say I wanted to take the square root of b, which is the square root of 100. Now we know what the square root of 100 is. We know it's 10. It turns out when you're working with logs, you never work with radicals. But there is a way of working with radicals and logs if you change your radical form to exponential form. Remember, you could write the square root of b as b to the 1/2 exponent. We did this when we discussed exponents at the beginning. We talked about, at one point, fractional exponents. And we said that fractional exponents is just a way of writing radicals. When we started our chapter on radicals, that's when we talked about this. We said if we had the cube root of b, it could be written as b to the 1/3. Etc. What we call the denominator of the fraction is what we call the index of the radical. When there's no index written in, it means the index is really understood to be 2. That's why it means b to the 1/2. So if we ever want to, so here's rule number 1. Anytime you want to deal with radicals, in this chapter, first change that radical to an exponent. If it's a square root, make it a 1/2 exponent. If it's a cube root, a third root, put it to the 1/3. If it's a fourth root, put it to the 1/4 power. Make it into an exponent, and then just use the rules of exponents, which means that if I have something like this is a sub-rule of rule number 3. If I have the log of base b of the, let's call it the nth root of a. What I'll do is I'll rewrite that as a log base b of a to the 1 over nth exponent. If the index is n, the exponent is 1 over n. And then just use rule number 3, where my exponent will become my coefficient. So that'll give me 1 over n times log base b of a. The exponent becomes the coefficient, because when you're dealing with logs, they are in fact themselves exponents, and we just use all the rules of exponents. These are basically, the log rules are, the properties of logs are really the properties of exponents. So the question is, how do we use this? So one of the things that we do with this is we use it to what we call expand logarithmic expressions into individual log statements. Let me give you an example, and then I'll do a couple of examples, and then I'll ask you to do one. So let's say I had something like this. The log base 3 of x squared y to the 4th divided by z. I have this expression where I'm telling you what I'm doing to the x, the y, and the z, and I want to write it in terms of what I should do to the logs. This is what's called expanding in terms of the logs. Now, here's what I do. My first step, I'm going to give you all the steps, is change radicals to exponents. If you have any radical in your expression, if you have a square root, you have to write it as a 1/2 exponent. If you have a cube root, etc., you change any radical to an exponent. Step 2, look for anything that involves multiplication or division. Now, in this example, I have two things multiplied, and I have something that it's divided by. I know in terms of logs, wherever I have things multiplied, I add the logs. Wherever I have some things divided, I subtract. So I'm going to expand this in terms of multiplication and division. So this is going to become log base 3 of x squared. Now, since this is multiplication, I'm adding the logs. Don't forget, I have to put the word log in front of each expression. So the next thing is the log base 3 of y to the 4th, minus, because I'm subtracting, the log base 3 of z. So any place I see a multiplication, I change it to adding logs. Any place I see a fraction, I subtract. That means I'm dividing and I'm subtracting the log. Then the third thing is change the exponents, make the exponents into coefficients. In other words, any place I see an exponent, I'm going to make it as, I'm going to turn it into a coefficient. So there's an exponent 2 here, it's going to have to go in front. There's an exponent 4 here, it's going to have to go in front. There's no exponent over here, it's understood to be 1, so I don't have to put anything there. So my final expression in this case becomes 2 log base 3 of x plus 4 log base 3 of y minus log base 3 of z. In other words, in front of each one of the expressions, I have to write this log base, whatever it is. That's why it's called expanding. But again, where I had multiplication, I add. Where I have division, I subtract. And where I have exponents, they become the coefficient. Do you think you're ready to try one like this? Here's an example for you to do. Okay, we want to expand this. This is called, I'm going to, can I erase what's on here? I guess I should. It's just, I'll leave this on. It's just too busy here. Okay, so we want to expand this. Here's the expression. It's called expanding into individual logs. It's log base 2 of 8 square root of x over y z squared. Okay, I'm going to give you a few minutes to try this out. Okay, remember the first thing I said to do is if I see any radicals, to rewrite the radical as an fractional exponent. So I'm going to rewrite this as log base 2 of 8. Instead of writing the square root of x, I'm going to write x to the 1/2 because the square root is the same as the 1/2 exponent over yz squared. In other words, the only thing I had to change in the first step is any radicals I see, I change to exponents. Then I go back and my next step is to look for anything that involves multiplication or division. And I see the 8 is being multiplied by the x to the 1/2. And the whole thing is being divided by yz squared. So when I expand this, it's going to be the log base 2 of 8 plus the log base 2 of x to the 1/2. Because when I'm multiplying, I add exponents, which means I'm adding the logs, minus, now notice I'm going to have to subtract the whole thing because whatever is I'm subtracting now, this is all in the denominator, it all has to be subtracted. So it's going to be the log base 2 of y plus the log base 2 of z squared. Notice I put it in parentheses because both the y and the z squared are in the denominator. Okay, the next thing is to look for exponents. Now there's an exponent here, so this exponent is going to become the coefficient. And this is an exponent over here, so it's going to become the coefficient. So the next step gives me log base 2 of 8 plus 1/2 log base 2 of x minus parentheses log base 2 of y plus 2 log base 2 of z. Notice I keep writing the word log base 2, log base 2, log base 2, log base 2. Of course, I have to close that parentheses. Two other things that I could do. First of all, this log base 2 of 8. we actually could figure that out. What is the log base 2 of 8? Well, it's hard to realize what it is in log form. So I'm going to put it, let's make it equal to a small a, and switch it from the log form to the exponential form. We're looking for what this a is equal to. Well, 2 to the a is equal to the 8 if we write this log format in exponential. Here's my base is 2, my exponent is a. 2 to the a equals 8. Now it's easy to realize that what the a is equal to 3. So therefore, instead of log base 2 of 8, I could simply write this equal to 3. So therefore, let's get this over here. This whole thing becomes 3 plus 1/2 log base 2 of x. Now, there's a minus in front of the parentheses. If I want, I could distribute that minus. It's as if multiplying by a -1. So if I don't want a parentheses, this would be minus log base 2 of y. And a minus times, this is like a -1 times a 2, minus 2 log base 2 of z. Notice anything that ended up being in the denominator had to be a negative log, because when it's in the denominator, it means we're really dividing. If I would have not put this parenthesis here, or if I would have just made that a plus, it would have looked like, in the end, I'm just multiplying by this z squared. I'm not. I'm dividing by the z squared as well. So this would be your answer in the simplest expanded form. I don't know if anybody got that answer, but it's definitely involves just using, basically what we were using were those 4 rules of what I call log arithmetic, or the properties of logs. Now, we're going to continue with this on Thursday, but what I do want to show you is one way what we've been talking about now could be used in solving certain types of examples. So I'm going to erase this and I'm going to go to another type of example that could be solved using logs. And actually can be used if we want to solve things using our calculators. If I gave you an equation that looks like this, this is an example of something called an exponential equation. It's an exponential equation because the variable, the x, is in the exponent. So how do we solve an exponential equation? Well, the easier ones to solve are the ones where it's possible to put both numbers on both sides in terms of the same base. The base that's being used here is 4. This says 4, base 4 to the exponent 1 plus 2x. See if you could put the number on the other side. Can you write that in terms of base 4 also? Can you write this number as 4 to some exponent? And it turns out that you can, because 64 could be written as 4 to the third power. And once you have both bases being the same, it's obvious that you don't have to worry about the bases anymore. What you're worrying about is the exponents. The exponents have to be the same also. So that must mean that the 1 plus 2x, which is this exponent of 4, is equal to the 3. And now you have a simple equation to solve. And that gives you 2x equals 2. So x equals 1. Your answer would be x equal to 1. If this was a multiple choice question, which it is, but if this actually was on a final, you could have just tried all the different answers and see which one made the most sense. They gave you, like if they gave you x is to 1, then you would see it works, whereas the x equals 2, 2 wouldn't work. So you could do it that way. So that's an exponential equation where it's possible to put both numbers in terms of the same base. But what if I gave you something like this? I'll do a simple one. Suppose I gave you 5 to the x is equal to, well, I'll start with one that's easier, and then I'll do one that's harder. 1 over 125. Okay, if we think about this, we know that 125 is 5 times 5 times 5 is 5 to the third. So this means 1 over 5 to the third. But this is a problem because this is not in the denominator and this is. So I really could write this as 5 to the x is equal to 5 to the negative 3. Because a negative 3 really means 1 over 5/3. And then actually, it's easy to see that the x is equal to negative 3. So again, we did this exponential equation by putting the 1 over 125 and the same base as this side. It was obviously using base 5. And I wrote it as 5 to the negative 3, and therefore I was able to get the two exponents equal to each other. What if I had given you this equation? Suppose I gave you 5 to the x is equal to 20. And I go to try to put 5, this side, into base 5. Well, I know 5 to the 1 is 5, and 5 squared is 25, and I totally skipped 20. 20 is not able to be put in base 5. You can't write 20 as 5 to some exponent. And if you think about it, in most cases, you can't put the two numbers you picked. You're only lucky if they both can be put in terms of the same base. Is it possible to solve something like this? And the answer is yes, by using logs. Here's what we do. Write the word log in front of both of these expressions. Log 5 to the x has to equal log 20. Well, that makes sense because if the two numbers are equal, obviously when you take the logs of them, they're going to be equal. Notice that the log I took, I didn't put a base here, meant that I was using log base 10. I'm using common logs. And the reason I'm using common logs is because my calculator has common logs in it. Now, since I'm now dealing with logs, I can use log arithmetic. And this exponent here, x, then becomes a coefficient. Remember, in exponents, in logs, exponents become multipliers. So this can be rewritten as 5 log x log 5 equals log 20. And now I want to get the x alone. Since it's being multiplied by log 5, I'll just divide both sides by log 5. And here's where I'm going to have to go to my calculator, because I can't do this. I don't know what the log of 20 is. I don't know what the log of 5 is. But I'm going to, in my calculator, press my log button. This is what I'm doing. Give you the instructions. Press your log button, LOG. Put in the number 20. It'll open up and you put in the 20 and close the parentheses. So putting in 20 and I'm closing my parentheses. Then I press my divide button and press my log button again. And I put in the 5 and close the parentheses and press equal. Exactly what it says there, log 20. Don't forget to close those parentheses, divide by log 5. And it comes out to 1.86. I'm going to go to 2 decimal places. 86, the next decimal number is a 1, so I just leave this 1.86. And we're not surprised that the answer didn't come out to be even, because we knew it wasn't 1, because 5 to the 1 is 1. It wasn't 2, because 5 to the 2 is 25. This is a little bit less than 2 because it's 20 and not 25. Notice I got my answer 1.86. I could have even, let's say you found this one difficult to do. Suppose you couldn't figure this out in your head. You could have done it with logs. You could have done it by doing the log of 5 to the x equals the log of 1 over 125. And again, make this my exponent, x log 5 equals log 1 over 125. And divide both sides by logs, the exact same way I did this. And again, in my calculator, I press my log button. Here's my parentheses. I do 1 divided by 125 and close that parentheses. That gives me the top. Then I divide and I do, again, my log button. And I put in my 5. And let's see what we get. Log 1 divided by 125, close parentheses, divide by log 5. And I press equal, I get -3, which is exactly the answer I got over here. So I'm able to solve that question using my calculator. So this is what's called solving exponential equations. We're going to learn how to solve logarithmic equations on Thursday. We will finish up this topic on Thursday. I hope to have specific information as to your final exam at that point. And I hope to be able to give you a practice final so that you can see what your final exam is going to be like. Okay, have a nice day and I will see you on Thursday. If anybody has any questions, I can stick around a few minutes if anybody wants to ask me any questions.